Yay! So we got secant x, tangent x, derivative of tangent. Secant squared x. Yay! Derivative of cosine. Negative sine. What's inside of the trig function? Still 8x squared minus 7. What's the derivative of the trig function?
16.
Or the inside anyway, 16x. Wait. So 16x. And then if you leave it like that, that's fine. If you don't like having the 16x thing at the end, you can move that, and I would move it to the front of the sine function. Just don't put it in front of the negative, because then you'll think 16 minus sine x, or whatever. It's still multiplying the trig function, so you could rewrite it like this, negative 16x times the sine of 8x squared minus 7. But either of those is totally acceptable. So if you just leave it like this, that's cool. And if you're going to move the 16x, make sure all of it stays outside the trig function. That's not inside the sine function. And don't put it in front of the negative, because then you don't want to accidentally turn this into subtraction when it should be multiplication. Any questions with that? All right, packet. We left off yesterday with the TV camera problem. Watching the rocket launch up vertically. And Lucas, could you please turn off the backlight switch for us? Thank you. All right, so we've got our camera on the ground, as we say, camera located at the ground level. All right, and we're filming a rocket rising vertically, and the position or height of the rocket is s equals 50t squared. The camera is 2,000 feet away from the launch pad, so the camera's over here, not right next to the rocket. And then the camera is following the path of the rocket. So the rocket is moving, so you're going to have a diagonal line up from the camera to somewhere. It doesn't really matter where you draw this diagonal line. Just don't draw it like flat across, because we want to have an angle here, because the goal is to find out how is this angle of elevation changing. So as you watch the rocket rise, your eyes have to follow the path of the rocket, and that's going to give you an angle. What's that angle doing? Any questions with putting together the picture and locating information on it? And then we want to find out how the angle is changing. So the goal is d theta dt, and specifically at 10 seconds after launch. So that'll kind of come into play later on. What's an equation that we could use to kind of relate the sides of the triangle that we have and the angle that we are dealing with? So when we do Pythagorean, then we're dealing with the sides of the triangle. Pythagorean theorem doesn't involve angles at all, right? So Pythagorean theorem is great if you're only talking about the outsides of the triangle. As soon as we get into an angle, then we're talking trig. So we got to think, okay, what trig function, sine, cosine, or tangent, is going to be best for this angle and these sides? Tangent. Why tangent? Is opposite over adjacent. So tangent of theta, remember SOHCAHTOA, because you're dealing with right triangles. So now this is right triangle trig, SOHCAHTOA, and tangent is the opposite over adjacent. That's your OA. So tangent of theta, and opposite side is the height, 50t squared, and adjacent side is 2,000. And you could call it S over 2,000, but since you know that S is 50t squared, probably better off just calling it that. Any questions with your equation? Now, once you got that, maybe nice to get rid of the fraction here. So how can we disappear the fraction? Just multiply the 2,000 over. So you have 2,000 tangent theta equals 50t squared. Actually, is there something you can divide by to make the number smaller? 50. Can you divide by 50? Let's divide by 50. What's 2,000 divided by 50? 40. Yeah, that's much nicer. So we have 40 tangent theta equals t squared. That's going to be a much nicer equation to work with. And once you've got your equation, you also then have to differentiate it. So what's the derivative of this thing? So secant squared, so we have 40 secant squared of, not yet. What's inside our trig function? Theta. But you're right, when we differentiate this, we also need to get a d theta dt. So we have to differentiate the inside of the trig function. The derivative of theta is d theta dt. So don't lose theta. That's still inside your trig function. Just like in the warm-up, we still have an 8x squared minus 7 inside the sine function. It's not a 16x inside there. The 16x is outside. Here, the d theta dt is outside, and you still have the same old theta inside. So that is your differentiating with respect to time. Over here, what's the derivative of t squared? 2t. Do we need a dt dt? No, because it's already t. So it's like, oh, it's already in terms of time. Hooray! Just do normal differentiation on that. If you really want to put a dt dt, go for it, and then cancel it out. So now we've got our derivative equation and our initial equation. Questions with either of those? Now what? Find theta. And yeah. So you come back here to find theta. So you might start filling stuff in and say, all right, I'm doing this at 10 seconds. So plug in 10 for t. So I have 2 times 10. And over here I have 40 is 40. Secant squared theta is, I don't know what theta is, so that's just going to stay d theta. And the goal is to find out d theta dt, so I'll just leave like that. So you say, I need to find out what theta is. So you come back over here, and you say, all right, tangent of theta equals t squared. I know that t is 10, so I've got 10 squared here. And square it, divide by 100. How do you solve for theta? Yeah. So you can reduce this and say that's 10 over 4 or 5 halves, but that still doesn't get you theta. So how do you kill tangent? Inverse tangent. This is now a calculator problem. So to kill off tangent, you got to do inverse tangent. And on your calculator, that's this thing, tan negative 1. And you do that, and you get some decimal. And does it matter if we're in radians or degrees here? Probably not, but let's do it in degree. No, let's do radians. Because when you go to solve for d theta dt, that's going to be in radians anyway. So let's just put ourselves in radians so that when we get here, it makes sense to us why we're in radians per second. Theta can be in either radians or degrees. I would recommend radians because when you find the rate of change of your angle, it will be in radians per second. Even if you do all this work in degrees, pretty sure that'll be in, yeah, it'll still be in radians per second. So just put your calculator in radians so there's a little bit less confusion. So if you have a calculator, you guys know how to go back and forth between degrees and radians? Does anybody not know how to do that? Okay, so George, okay. On your calculator, you see up at the top where it says mode? Push that button. Then like the third line down, you see radians and you see degrees, right? Which one of them is highlighted? Degrees? Okay, go down, highlight radians, hit enter. Cool? All right, cool. Now you're in radians. Now, when you go to my brother's class, as soon as you walk in the door, put it back into degrees. And then when you come back to my class, when you walk in the door, put it back into radians. Anybody else in physics get into that same habit? Or just get 2 calculators, one for math and one for physics. That is a lot of money. Don't do that. So, yeah, you should be in radians in math class most of the time. So when you do inverse tangent of 5 halves, oh, do you guys know how to make tan inverse happen? The tan negative 1. Does anybody not know how to make that happen? Okay, cool. So what is that? 1.19? So right now, our angle is 1.19 radians. So now we have something to take back into the derivative equation, and we can now solve for d theta dt and see how is that angle changing. So over here, you might say that's 20, 40, and then secant squared of 1.19 times d theta dt. And what do you do now? Divide, so divide the 40 over. And do you have a secant button on your calculator? No. Let's try to avoid secant. How can you get secant over here? How can you get the secant function to the other side? Yeah, it'll become cosine. So you say, well, if I divide by secant, what's the reciprocal of secant? Cosine. So instead of dividing by secant, I can multiply it over here and make it cosine, because that's the reciprocal. So when I do this, d theta dt equals 20 over 40 is a half. Secant squared comes to the other side and turns into cosine squared of 1.19. And now you can look at your calculator and say, all right, I do have a cosine button. Now, the way you deal with a squared is you do cosine of 1.19, see what that is, and then square it. So what you might type into your calculator is 0.5 times cosine of 1.19 squared on the whole cosine function. Or if you want to break this up into smaller parts, do cosine of 1.19, get an answer, and then do 0.5 times the answer squared. And whatever that answer is. So that's kind of dealing with this. Like, I don't like secant. Yeah, I don't either. Multiply it to the other side, now it's cosine. Great. And then you can evaluate the cosine function, see what you get, square it, times by a half, and you got your angle, how it's changing. What is that number? 0.069, and our units are radians per second. So even if your angle is in degrees, the rate of change of the angle will be in radians per time. Because the angle itself in the cosine function might be radians or degrees, but once you've done the cosine or sine or tangent value of it, the units are gone. And you just have a number, and that's what radians are. So when you find the rate of change of the angle, it will always be in radians per something, and so unless you're given an angle in degrees, just assume everything's in radians to kind of keep that simple. If you see degrees in the problem, then you kind of have to go to degrees. Yes? It's fair. Just talk about it. So I wrote over here the different types of related rate problems. There's just the generic XY stuff with no context. That was like 1 through 7 of your homework. You had 1 through 5 and 6. No, 1 through 5 and 7 due yesterday, and then 6 is due tomorrow. Then you have your shapes: squares, circles, triangles, rectangles, spheres, cylinders, and so on. If you only have one independent variable, like with circles and squares and cubes and spheres, then great. If you have two independent variables, like radius and height, for example, with cylinders and cones, then it's a little more complex, and try to look for a way to like substitute one of them out in terms of the other with a ratio. So that is like numbers 13 to 22 from the homework sets. I don't think you're doing all of those problems, but you did a lot of them last night, and you have a couple more for tonight. Then there were the distance formula problems where you had like, hey, what's the distance between this point on the curve and the origin? And we did a couple of those on Monday or Tuesday. So that was like 11 and 12 of the homework. And then there's the triangle problems, and there's a variety of those. So those can be Pythagorean theorem problems, which we did a little bit yesterday, and we'll do more in a second. They can be trig problems, where you have an angle involved. or they can be ratio problems where you have like similar triangles and you're just talking about the ratios of the sides of the similar triangles. So we'll look at that today too. So my goal is to finish the packet today and then give you guys time to work on the homework together in class, whatever time we have left. Tomorrow we'll go over the homework. I have another packet of way more problems than what we're going to do. And I'll give you guys time tomorrow in class to work on that as well. And maybe also on Monday, because I think at this point we'll have gone over pretty much all the different kinds of problems by the end of class today. And then you'll need time to practice and discuss with each other, and I'll just kind of putz around and help where I'm needed. Maybe. And then your quiz, is that your question? I'll give formulas that are not the Pythagorean theorem. You should know your Pythagorean theorem. I'm not going to give SOHCAHTOA. Right? So like these formulas here, you got to know your SOHCAHTOA. You got to know your Pythagorean theorem. And ratios are just fractions. So it's not really so much a formula as like you make a fraction, you make another fraction, and you put an equal sign. The geometric formulas I'll give you. And distance I'll give you. So I'll give you distance, I'll give you geometric formulas. I won't give you triangle formulas because you should know your triangles. You saw triangles geometry, you saw triangles in pre-calc. You've seen triangles since you were like 4 playing with shapes and stuff, so you should know your triangles. Fair? No? Too bad. And quiz, I'm thinking probably Tuesday or Wednesday next week. And I know we have short classes because of Keystone, so I'll make the quiz not like full-blown hour-long quiz, I hope. So move on to the next page, and you get to kill me. Or at least attempt to. So that's, cathartic. So go ahead, read the problem, draw a picture.
I know That's
They gave that to me,
oh.
but it was gone for a while.
Wait, in what direction am I falling?
Oh, other than down.
Other than down?
So like, okay, say if I'm pulling the ladder.
Yeah. So,
I'm pulling the bottom of the ladder towards, like, away from the house, right?
yeah. So here's your ladder, right?
Yeah. And it's leaning against the house.
Leaning against the house. You see that? Let's play that game again. Alright, so see the ladder? Rachel comes along, pulls the bottom of the ladder away from the house, drags it along the ground. Look at what the top of the ladder does.
Okay. That makes more sense.
That was so much fun. I could do this for the rest of the day. So what's the top of the ladder doing? It's going down, scraping my face against the stucco on the house. Right? It's great. I'm going to come down. Before I hit the ground, I'm already in pain because like my skin has been ripped off my cheek. So it's good stuff. Now I'm gonna like get my ladder and come up and like whack it. But, assuming I can still walk. This one's better. It's a little thicker here. So maybe that helps you kind of see what's going on. If you know, when in doubt, go get a ladder, lean it up against a house. What?
Watch them fall.
You just imagine somebody's up there, like a ghost person up there, like a ghost runner in baseball. All right. Anybody want to draw their picture for a board point?
I need.
Prince, your hand was up first. Go. Now, if you're wrong, I get to whack you with this thing. So.
You drew to that side?
I drew it to the left. I don't know what's wrong with you. And you're gonna accommodate that? You're gonna cave to that sort of passive aggressive comment?
Called peer pressure. What? Hello?
You're calling a vertical thing X?
Ladder.
Do I get to have arms?
No.
Okay.
You're right.
Isn't the length of the ladder?
I'm writing it.
I wanted the 2 feet per second be the base, the bottom. Not the-
He's trying his
I
best.
think I understand where he means to have the 2 feet per second to be. He just in his picture didn't do it very clearly, so I know what he's talking about. He's referring to that arrow down there.
Yeah.
All right.
What's speed?
Cool. You can do some thumb exercises for that. All right, you don't get whacked. Any questions with this drawing other than why I'm armless? Seriously, like where are my arms?
It makes
Where's
it
the
easier for
person
you to
pulling
fall.
the-
Where's the person for you? Is he just moving on his own hard? Yeah.
All right,
He's
all right.
his teeth. You know?
Here, I got that one. Anyway, so we have the sides of the triangle. 50 feet is the hypotenuse. Y is the height. Currently it's 15 feet. Is this Y going to be a variable, or is that always 15?
No,
It's changing because, let's get another arrow on here. What's happening with the top of the ladder? It's going down, so let's put another arrow right here. What are we going to call that?
A wall?
A wall. Yeah, what are we going to call this arrow? Like, so that's dy dt, right? Because that's how the height of the triangle is changing, and that's the goal. What should we call this 2 feet per second? Dx dt, which implies there has to be also another variable.
T.
We have a y and a dy dt. We have a dx dt, so this should be probably x,
Oh, that's it.
right? So this base side right here is also changing. It needs a variable. Anything that's a changing quantity is going to need a variable. So the y, the height of the ladder, or the height of the me up there, is a changing value, so that needs a variable y. The distance from the house to the base of the ladder is changing because you're pulling the ladder away from the house, so that needs another variable x. Is the 50 changing? The length of the ladder? No, that's not. The ladder is not telescoping while we do this. That would make things a little more complicated even than it already is. So I think we now have all of our components. We have the sides of our triangle, x, y, and 50. We know what y is right now, but that's changing. We know how x is changing, and we want to find out how y is changing, right? Any questions with all that? Put it together, what's our equation? That's a good start. X squared plus y squared equals 50 squared. So it's just another Pythagorean theorem problem. How do we know it's Pythagorean theorem? Well, look at the shape. What is it? Right triangle. And we're talking about the sides. So right triangle, we're talking about all the sides. There's only one triangle. There's not like another similar triangle to deal with. So it's Pythagorean theorem. And what's the derivative of this thing? 2x dx dt plus, so 2x dx dt equals 2y dy dt equals 0. And now you're in business. So you have your picture, you have all the components to the picture, you can use those to create your equation and your derivative equation, and now you're on your way. Let's start filling stuff in. So 2 is 2. Do we know what x is right now? No, so that's what we don't know. So we're going to have to find that out. Do we know dx dt? Yeah, that is 2. Now, is dx dt positive or negative? Positive, negative. So why do you say positive, positive person? Yeah, because x is increasing. So you might say, oh, you're pulling the ladder to the left, and the left is the negative direction. Fair enough. But as Prince started to do, you could just as easily have drawn it to the right. So since x is increasing, dx dt has to be a positive value. So that's a plus 2. Plus 2, do you know what y is right now? 15. Do you know what dy dt is? No, that's the goal. So we just got to figure out x. Come over here and find out x. So x squared plus 15 squared equals 50 squared. Help, what's 50 squared? 2,500. What's 15 squared?
Yeah, you're on your own.
225. 2,500 minus 225 is 2,275, 2,275. Square root? 47.7, you said? All right, so now you have that. Plunk it in here. So we have 2. I'm going to write a little bit bigger. 47.7 times 2 plus 2 times 15 times dy dt equals 0. So what's 2 times 47.7 times 2? 190.8, all right? That's 30 dy dt. So you solve this, and what do you get? $6.4. All right. So negative 6.4. What are the units? Feet per second. Done. So I'm falling at a rate of 6.4 feet per second. And we could do this again later on. So like right now, the base of the ladder is only 15 feet away from the house, but the ladder's 50 feet long. So if you keep pulling this, and you just not, it's not just a game, but you're going to scare me. It's like, no, I'm really going to kill you. And you pull this all the way out to like 49 feet away from the base, then this would be 49 for y, and a much smaller number for x, and you'd have a different value. So you can see if we did this a couple of times, how my speed changes as I fall, and you'll see that I get a lot faster by the time I hit the ground. We could probably do a limit with that, find out exactly, but let's not. Any questions? All right, so that's ladder problems are fun. I can almost guarantee a ladder problem on your quiz because ladders are really awesome. I hate ladders. All right, shadows. Last one on this packet. Try to draw that. So this one, I think, is hard to visualize and kind of make sense of and get set up. but then the actual math and calculus is easier than all the other problems. I'm curious how fast is that in like miles per hour? All right, so 5 feet per second to miles per hour. It's only 3.4 miles per hour.
It depends on your leveling. We saw people walk past.
Yeah, this is going to be a ratios problem.
Okay, nice.
So, anybody want to draw a picture for a board point? Risa? Yeah, this one's harder to visualize. Once you see how it's set up, it's not so terrible, but setting it up is really the hard part. I could make this like a bonus question sort of thing. There's a variety of shadow problems. There's a shadow where like there's a dude walking away or towards a lamp or a sun here. Here's a lamp, I'm over here and I drop a ball, and then there's the shadow of the ball on the floor traveling towards the ball as it falls. So that's a good problem. I think that's in the textbook actually. The very last problem, yeah, number 53 in the book is like that.
Yeah, those are like a street lamp.
Yeah, like one of those street lamps you walk past in the morning, it like turns on or off.
Bryce, I believe in you.
I think you never know. You never know if it's in the future or not. You never know.
Mm-hmm. So, yeah, so here's a good lamp. Here's the lamp. Where's my shadow? Like over here, right? Yeah, hey, there he is. So if the lamp is over here, and the shadow is going to be over there, right? So you drew your lamp, and then your shadow is going towards the lamp. So that's fun. Like maybe that's how vampires work. So we would need to kind of readjust this, maybe to move the lamp over here, and then it would make more sense. And what's especially tricky here is that we actually want a smaller triangle with the dude being the height, and then a larger triangle where the lamp makes the height. So let's try to redraw this, kind of making those adjustments. We're going to have two triangles. One is going to be small and kind of inside the other larger one. So here's our lamp, which looks suspiciously like a sun, but okay. And here's our person. And the lamp looks at the person, and then the person casts a shadow on the ground, right? So we have that. So, boom. So now we have the height of the person. That's 6 feet. Let's assume that doesn't change. We have the height of the lamp. That's 15 feet. Let's assume that also doesn't change. And then we have the shadow. We'll call that S for shadow. So the dude's shadow is from the guy out to the end of this triangle, right? Because if the lamp is further down, like think of a setting sun. Like as the sun sets in the evening, what happens with your shadow? It gets really long, right? So that's because if the lamp is like there, it's looking through you at this angle, and it's a much shallower angle, and so that's why your shadow gets so stretched out. If the sun is way up in the sky at noon, then it looks right down on you, and then you have a really tiny shadow right here. So that's kind of, yay, shadows. So the sun basically looks through the top of your head, and then whatever this triangle is, the base is your shadow. And then we want to talk about how the shadow is changing, and that's just the base of the small triangle. And then we also want to talk about the tip of the shadow, which is a little weird, but that is really talking about this whole big distance. I'll call that big T. Because as you walk further away, or I guess towards the lamp, your shadow is going to change, but also the big T is going to change. Say again? Oh, yeah. So you also know that this right now is 10 feet away from the base of the light. So this is 10. Yes, thank you.
Why wouldn't the tip of the shadow be like the angle edge to the right? Yeah.
So it is, but the way that this is moving is the same as how this whole distance is moving. So when this point changes, it changes the entire distance from back to the base.
Okay, so you wouldn't use trig for B.
Nope, no trig. So all of this is just going to be proportions. It's going to be ratios. Yes. Yep. So when the tip of the shadow moves, the tip of the shadow all the way back to the lamp is this big distance T, and that distance is going to change exactly the same as how the tip of the shadow moves. So if we can figure out how this big distance changes, then by extension we're also figuring out how fast the tip of the shadow is. That's the part that's kind of getting your head around that is a difficult thing. There's also like the overlapping stuff, which is not easy. So let's get rid of this so we have some space to write equations. So we have two similar right triangles now. We have an inner right triangle and a bigger right triangle. So in the inner right triangle, base to height, what's the base of the little right triangle? S. And what's the base what's the height of the little right triangle? 6. And that's going to equal the same ratio, but in the big triangle. What's the big triangle base? T. And what's the big triangle height? 15. And then you look at that and you say, oh, we have two variables that we don't know. We don't know S and we don't know T. But we can create a direct relationship between the two of them. So there's another equation that we can make just using the bottom of this triangle. How do S and T and 10 all relate to each other? Yeah, you could say T minus 10 equals S. Or you could say 10 plus S equals T. So relate the 10 and the S and the T all together, and that gives you two equations, and now you have a system of equations. You have your ratio equation, and then you have your secondary equation of just relating the overlapping bases together. And then guess what you do? Before you solve, before you do that, differentiate. When you differentiate big T, what do you get? Yeah. dt dt. delete, back up. See this 10? If you're walking away from the lamp, is this distance always going to be 10? Okay. What should we call it? Call it x. That works. So call that x, and we can say x equals 10 right now, but it isn't always 10. Because as you walk away from the lamp, the distance between you and the lamp is going to change. So that needs to be a variable. Which means, over here, instead of t minus 10, we should call this t minus x. All right, now we're in business. So you go ahead, you still are going to want to differentiate. And what do we get when we differentiate? dt dt minus dx dt equals dx dt. And you only know one of these, right? You know dx dt. Because that's how fast this guy is moving. So as he walks out here, that's going to change the shadow, and it's going to change t, but it's going to directly change x. So dx dt is 5. So as you walk away, that's changing the distance between you and the lamp at that rate.
How do you find?
He walks at a rate of 5 feet per second away from the light. So you could fill in dx dt over here. But since you don't know these other things yet, you can't solve that. So let's go over to the ratio equation, which I was trying to avoid because it's got fractions, and we know we all hate those. But we got to deal with it. Cross multiply, right? We got 15s equals 6t, and then differentiate. And what do you get when you differentiate? So 15 ds dt equals 6 dt dt. And what I would probably do now is just substitute. I know what ds dt is over here. Let's plug it in. And then you can solve for dt dt. So all the calculus, like the differentiation stuff, is super easy. Everything else about this is really hard. So we say 15. We know ds dt, it's that thing. dt dt minus 5 equals 6 dt dt. Distribute. Yeah, 15 dt dt minus, what's 5 times 15? 75, thanks. Subtract. Add 75 over, and what's 75 divided by 9? 8 point, somebody said 3, 8.3. That's 8.3 feet per second. So that's how fast the tip of the shadow is moving. Once you've got that, plug it back in over here and find out ds dt. So what's ds dt? Yeah, 3.3. Ugh. So kind of visually and all the interaction between the two derivative equations is tough because you have, I got two kind of initial equations, one relating the sides of the base, like all the base stuff, and another relating the ratios of base to height of the two triangles. And then you have to work with their derivatives, each of them kind of back and forth. I think these are tough. I think these are the hardest problem that we look at kind of conceptually. Some of the other things can be tougher, like the cones and stuff and the cylinders with keeping track of R and H, and maybe have to be product rule. But I think this is the toughest thing that we look at here. Any comments or questions about any components of this? Yes. So this is the answer to B, and this is the answer to A. There's not just this one way to do it. There's other ways to attack this. This is kind of where our discussion took it. So this is the way we did it. But there's other ways to do this that I've done in the past that are not really any easier, but get you the answers in the opposite order. So when they say for this kind of problem, what's part A and what's part B, I wouldn't get wedded or like don't like really fixate on A then B. Kind of think of it as like it's all happening together. And the way you attack it might dictate actually you get answer A before answer B or vice versa. Laura? This would be a bonus. So if you saw something like this, it would be a congratulations, you have some extra time, get some extra points. So x is 10, but the x dt is 5 because that's how fast you're walking away from the lamp. So x is how far you are from the lamp right now. The x dt is how fast you're walking away from the lamp to make that get bigger. So that's why over here, when we have dx dt, we use 5 instead of the 10. It turns out you don't use the 10 ever. So it doesn't really matter what x is. What matters is how fast you're walking. So no matter where you are, as long as you're walking this fast, this is how fast you'll be changing your shadow length and the distance away from the shadow to the tip of the base. Tip of the shadow to the base. Anything else? All right, so you have homework tonight. It's 5 problems. Number 6 is like that generic XY stuff that has no context to it. You need to do a little bit of quotient rule to get your derivative, but otherwise it's very straightforward. Number 12 is one of those distance problems using your distance formula. Number 9 is just kind of thinking about a line and how things change on a line. 16 is a sphere problem, and 25 is a ladder problem. And in 25, I think you're only doing part A. So don't worry about parts B or C. Actually, C I should have assigned as well, but too late. So 25, you're just doing part A. And then tomorrow, we'll go over that, and then I'll have your next set of problems for you guys. And it'll be more of, here you go, work together on stuff. And your homework over the weekend will be from this packet that you'll get tomorrow. How are you guys feeling about related rates? No?
It's not. It's the last two like were
The
really
shadow
hard.
problem.
Okay, forget the shadow problem. How do you feel about the stuff before the shadow problem?
Only the triangles I'm having trouble with setting up how
Okay.
to actually do it. Like which part is like the base and which part is like the height.
Okay. The book is helpful. They'll give you the pictures.
Yeah.
This is gives you some of the pictures, but not all of them.
Okay.
But I would recommend you try to kind of do things without looking at the picture, see what you can draw yourself for these, just to get practice with that.